Now, when I'm doing this, let's see. I thought about that. I usually do it with 2 screens. We'll do it with 1 screen. It's good enough. All right. And it may actually come out that way. So we're recording. So you'll hear. All right. Crankcase explosion, scavenging air fires. It is a subject that we need to talk about. Primarily, by the way, this is of less occurrences on slow speed. But when I've talked to Bill Davidson, the chief on the Bear, on medium speeds, he told me he's been through 4. These are major occurrences. This is not something that you forget readily. Crankcase explosions are a big deal, and they are preventable. Now, one of the things on a crankcase explosion, on the Bear, our medium speed Enterprise, you're keeping a slight vacuum on the crankcase, agreed? That is true with some of the medium speed propulsion engines, but not the majority of engines out there do that. Most of them have just atmospheric pressure in the crankcase. Normally, the mixture is over-rich. What do I mean by over-rich? Too much fuel and not enough air. To have an explosion, the conditions have to be right. Agreed? All right. Typically, what you're looking at is an overheated bearing is the primary thing that triggers a crankcase explosion. That overheated bearing, the oil comes in, hits that hot bearing, and comes out vaporized, right? And that's your fuel source. But again, you have to get that point hot enough to then be your ignition point, agreed? When it hits the ignition point, primarily the mixture is over-rich, and what happens is you have a minor explosion because there's not enough oxygen. Now, one of the things on this big slow speed, whoops, take a look at the side of the crankcase doors. Right? They're 6 foot high, 2 or 3 foot wide. By the way, when you take those doors off, it's permissible to take them off with an air impact, the nuts. It's not permissible to put them back with an air impact. Why? When you put them, the same thing, by the way, watch them when they put the tires on your car. There are some impact wrenches that are set with a torque, but I've also had them use an air impact and put my tires on, then I had a flat, and there was no way in the world I could get the nuts off. I bent the tire iron in a U, jumping up and down on it, trying to break it free. I was a little mad. They should be putting your tires on with a torque wrench, right, and checking them. If they don't, go home and check it and make sure that you can get it off. But anyway, the same thing here. If you're using a standard air impact and you put them on, you can snap the stud off the crankcase. So you typically, if you're using common sense, you barely tap it up and then take a normal wrench and tighten them, right? But anyway, look at these large doors. If you have a crankcase explosion, typically the first thing that happens is that overpressurization will open a door. Now, once that door is open, that engine can then suck in fresh air into the crankcase, and the secondary explosion has been known to kill anyone in the engine room. Right? That has happened, depending on the severity. The primary explosion is typically minimalistic. The secondary explosion is the one that has the force behind it. Now, when you're talking about this too, the way that you dissipate that primary explosion, and the first thing is to prevent this, right? Let's actually talk about that. How do you prevent crankcase explosion? On a trunk piston engine, make sure that your rings are in good shape and your combustion chamber is in good shape. If you're having bad injectors or low compression on a trunk piston engine, that unburned fuel can get down in the crankcase and can also be the fuel source. Right? Why would I not have to worry about that on a crosshead engine? You got the piston rod seal. Agreed. So one of them is bad operating conditions of the engine. Bad combustion can give you unburned fuel that can get into the crankcase. The biggest one is an overheated bearing. Now, the regulatory agencies will tell you that you can have either a oil mist detector, which does the Bear have that? Okay. Oil mist detector or bearing temperature monitors, which the Bear also has, and you test while we're out on cruise, even on the running gear, right? It's got a little arm that flips out if the bearing overheats to trip an alarm, right? So the bearings on the Enterprise engine are protected by this. The regulatory agency, you can have either. You really want to have both, right? Both is really good. The problem with having the temperature monitor, like the C10s have this problem, or any of them can have it. If you have a bad connection to one of these temperature probes, what will happen? The temperature will go all the way up or all the way down, the indication, and you'll get a shutdown in the main engine. So one of the disadvantages with doing the temperature is any probe malfunction will typically shut down your engine immediately, and you will not start it up until that malfunction has been rectified. That's a problem with it. The oil mist detectors are not always dependable. The oil mist detector is actually pulling gas out of the crankcase and putting it past, typically type some sort of an electronic eye to see how much mist is in there, right? You get false indications on the Bear. Right? Now, one of the things on this too, though, on the other side of this engine from this picture are your explosion doors, and we'll talk more about that in a minute. But those are designed, the explosion doors, over a certain engine size, you have to have explosion doors. That primary explosion is vented out those explosion doors, and then they reseal to prevent air getting back in, right? Okay. One of the things, I was on the President Arthur, and the oil mist detector would go off, and I would go down and check it. Just looks like just like the one on the Bear between the cylinders, right? And I'm looking at that, and when I look down, there's about a, I don't know, 2 foot, 3 foot diameter explosion door, and the other one's over there. Didn't think much about it, and then we get some communication, and unfortunately, especially between foreign and American crews, same company, a lot of times they don't exchange information, which I really don't understand why they're so worried about it. But all we got is a report that 3 of the new APL ships had crankcase explosions, brand spanking new engines built in Korea. The Koreans had modified the German design, and they were having crankcase explosions on number 3 bearings, brand new. The one of them, the first, they said, got knocked out of his shoes. The force of the explosion knocked him out of his shoes, and he died. And I'm sitting there looking at this oil mist detector going, oh, I know how he got killed, right? One of the things on that, if that oil mist detector is situated between those, is that safe to go check it? Right? It's not safe to. Now, the interesting thing is I've been at a Burmeister Wayne conference where the port engineers brought this up. Why is it getting put on that side of the engine? And their response was, that's the builder's, the shipyard's responsibility, not ours. Which is a cop-out in my opinion. But just think about that. The other thing that can cause a crankcase explosion, these Burmeister Wayne, there's a big chain drive in there, right? Those chain drives, just like your bicycle chain, it has a slack adjuster, if you want to call it that, right? That takes the slack out. You have to adjust the chain on a regular basis. If you fail to do that and it starts flipping back and forth, especially if it starts hitting the crankcase. There is an area where if it's flipping too much, it can hit the crankcase and cause sparks. That can cause a crankcase explosion. If the links break and the chain just flips down into the bottom of the engine, that will typically cause a crankcase explosion. There's other ones too. I think Doug Rigg had a picture on his door where a ship put the crosshead together and they put everything together, and they put the nuts on for the crosshead, and then they went to bed, and another crew came in and finished, and they thought they'd torqued those bolts down, and they hadn't. So the whole crosshead came apart, and one of the connecting rods was sticking out the side of the engine. That, believe me, caused a crankcase explosion. Right? So one of your primary one is, and one of the things too, when we get maneuvering, a lot of times the students are not monitoring the engine. When you maneuver, what's your primary concern? You keep the lights on, right? And you keep the propulsion on. Agreed? The main engine, someone has to be dedicated to the main engine 100% of the time, and you are looking at bearing temperatures and all that kind of thing. Okay? So these are the explosion door on the Burmeister Wain on the side here. And again, those are designed to open and then shut to allow the blast to dissipate into the engine room and then reseal and not allow air back in. So, overheated bearings, excessive piston blow-by, seize pistons. You seize a piston, it can do this too. This is trunk piston again though. Broken camshaft chains, gland rings on the slow speed. If the gland ring seize on the piston rod, that can also cause it. Now, with the explosion doors, it should come out as a superheated gas. That superheated gas, though, is plenty hot enough to, if you're enveloped in it, you're toast, right? Not only your skin will burn, but you're going to inhale that into your throat, and your lungs will be damaged also. If it can also come out, depending upon, this has a wet gauze on it, right? It has a gauze that's supposed to quench it. If it doesn't quench it, you'll come out with fire. Anywhere on that side of the engine, you're at risk. So if there's any way you're thinking that a crosshead or a crankcase explosion could be happening, you stay away from the side with the crankcase explosion doors. This is the same as this one here. By the way, you notice these are designed to deflect it off the deck plates, isn't it? So you're down on here. In some ways that may be better, but I don't know. But here is the gauze I'm talking about. And what it is, it's just like your fuel oil vents. You've got a bunch of different mesh. And the idea is the flame, as it goes through that, the flame will quench. Your gas temperature is not going to change much, but the actual flame will go out. And then these doors, the spring holds it closed. This door opens, and there's a seal around it that reseals. Now, your job as third, a lot of times, will be to check these. Agreed? Make sure you're very confident when you do this. Your life does depend on it if it happens. And again, these are not a common occurrence, but it does happen. So this is test equipment. Now, the one thing that they've mentioned too is, unfortunately, Burmeister Wain doesn't, or I'm not sure about Sulzer, but I know Burmeister Wain does not make their own valves. They farm it out. And some are good and some are bad. But there's it initially. You can see right here where it's initially opening. When they open and discharge, you do get a flame front come out of them a lot of times. And again, on the simulator, how do you prevent this? You need to be watching all your bearing temperatures. And if you see an overheated bearing and you get an oil mist detector, you need to slow down and contact the bridge and tell them you've got an emergency. Most of the time, too, unless it's imminent, you contact the bridge first and say, because you don't have your hand on the throttle, they do, don't they? And contact them, and you would tell them that we have a dangerous situation, we have an overheated bearing, please tell the captain we need to immediately slow down, and contact the chief. Right? And then typically what will happen, let's say you're just leaving port, and it's safe to do so, you would turn around and go back into the port and drop anchor. Or if you're out at sea, you would typically slow down, stop, and go in and check what's going on, unless you're in rough water. And then what you would try to do is slow down enough to protect the vessel and not explode. But again, you've got to watch your bearing temperatures. And this is a standard oil mist detector like you have on the Bear. And it's going cylinder to cylinder, and it's taking a sample of the atmosphere in the crankcase and looking for mist. Now this is an actual of a crankcase explosion, and I might turn the lights off on this with the, so you can see it better. It's kind of dark. It looks better when you look on it from Moodle, you know, on your own computer. But this is an actual, this was a crankcase explosion on this British Velour, which is a crude oil carrier, right? So, underway, full load of crude, 2 detonations from the engine room. Now, fortunately, this was unmanned at the time when this happened, so nobody got killed. The alarm history indicated that it only, the automatic shutdown of the maiden occurred 19 seconds after the activation of the first alarm. So this happened quick, right? You had a number 1 cylinder outlet temperature high, fire alarm, file detection failure, crankcase oil mist. And they had both the primary and secondary. They shouldn't have had the secondary. The automation did shut the engine down. The secondary occurred because they are not maintaining the engine and the explosion doors. Somehow it was able to breathe. Now, like I said, it's hard a little bit on here to see, but the upper part of the engine room is all blackened on the turbocharger side. Same thing with the plates. There's your doors. See how black they are? They extruded fire. I want you to think about, with 1/4-inch plate steel, the forces of the shock wave coming out of that to bend 1/4-inch steel like that. Or 1/8-inch plate, right? Deck plates. This one is the upper engine room. Look at your lights. In the uppermost part of the engine room, the heat was still so hot as to actually melt the lights down. So if you're in that space anywhere near that, you've got a problem. The ventilation ducts are crushed by the pressure wave. Now, the root cause of this is poor maintenance of this engine. They literally they had a bad injector is all it started out at. It was hitting the top of the crown. That caused erosion of the crown. There was a hole through the crown of the piston, and this is an oil-cooled piston crown. So that gas was then going into the interior of the piston and then down through through the piston rod and directly into the crankcase. So your combustion chamber had direct route into the crankcase. So what his fingers are in right there, see the cracks? That's the size of the hole in the piston crown. That right there, that's what you remember from Diesel 1. That's how you checked your piston crown for wear. Look at the gap from there to there. That's horrifying. You're supposed to be like 2 millimeters. But see the hole right there. So literally what happened, when the crown breached, the gases went down the piston rod, and then on this particular engine it comes out and drains down into the crankcase. So instead of the oil, well, there was some oil coming down there too, right? But it went down that normal oil path and a direct access. Okay. Now, the other one I want to talk about a little bit is scavenging air fires. Scavenging air fires are a little bit different subject, but again, it's one of the things that can happen to you. Primarily 2 strokes. Scavenging air fires are not typical on 4-stroke engine. They're primarily, though they can occur. A scavenging air fire is, you've got this, let's actually go back up again. That's why I put this in. Here's your scavenging air receiver, right? And then I call this the under-piston scavenging airspace, the space around the liner, the bottom end, right? You have cylinder lubrication that lubricates the rings. Now, if everything is right, all that oil is burned away, and there won't be much sludge down at the bottom. But if you have excessive lube oil delivery, not only is it a waste of money, but that oil can collect down here. The other thing is poor combustion, right? Products of combustion accumulating in here. So you get an accumulation of oil products in the scavenging air receiver and underneath the pistons. There are drains in these areas, but you have to make sure they're open. When you go in there and work in these, they're not super bad, but basically you come out looking like someone mopped the deck with you, right? You go into these areas. By the way, if you have anything rather than a buzz cut, you want to take and put rags around your head. You smell like oil for about 2 or 3 days if you don't. I mean, you wash and wash, and you still smell like oil. The other thing on this is you don't go into those spaces with clothes that you plan on wearing again. We would actually used to have one washing machine in the engine room specifically for these clothes that we did there. You wouldn't want to use it for anything else because there was so much oil and stuff with it. Or your generation, what do they call it, the Tyrex? Those don't work. Well, what I don't like about them is they rip really easy. I had an embarrassing moment with that. And the other one is they're like wearing a plastic bag, right? But anyway, a scavenging air fire is caused by an accumulation of product, of flammable material in this area. Now, the other thing I want you to think about when you scavenging air fire when it's running. Oh, by the way, on a 2-cycle, typically a lot of times is excessive. It can be excessive cylinder lubricant. Again, bad combustion. The other one is on certain engines. The one that I know that's prone to it is the opposed piston, Fairbanks Morse, running at low loads. They don't burn quite as well at low loads, and then you can get combustible products collecting in there. But it's a limited amount of fuel, right? It's whatever is collected, and normally if your drains are open and you make sure the drains are clear, it should drain away and it shouldn't accumulate. But if you do have an accumulation, all it takes is a piece of carbon to fall out of that port and fall into that. And I want you to think about when you start a fire, you've got 35-pound air, scavenging air, blowing right about 2 to 3 bar, 30 to 40 pounds pressure, blowing into that cylinder, don't you? Isn't that usually when you blow on a coil, you get coal, thank you. You get a nice fire. You get a piece of any material that drops into that's flaming, right? It can ignite that. Now, one of the primary things on a scavenging air fire is you can get turbocharger surge. Turbocharger surge is a breakdown of air delivery. So basically what happens is that compressor is pushing air into the cylinder. And when you get into turbines, and we don't have time to go into this in detail, but you know how a wing can stall? Both steam turbine, gas turbine, and centrifugal air compressor blades can go into stall. So it's a stall condition. It doesn't pump. That 3-bar air is coming back out. Then the pump does able to catch air, and it starts pumping again. So you get this very rapid failure and pickup of the air delivery. And it literally, one of the things we talk about is barking. If you've ever been sitting next to a turbocharger that's about 3 to 4 foot in diameter, 4 or 5 foot in diameter, in fact, and it starts barking at you like a dog, believe me, it has a reaction. I had this happen to me on the C-10s. I'd never heard it before. And when I got up to the control room, they'd been watching me, and it went into turbocharger surge. And they were all laughing and telling me I'd lifted off the deck about 3 feet. Scary. I mean, it's a loud, loud, loud noise. So one of these things, if you get a scavenging air fire, that's going to interrupt turbocharger delivery, and you can get surge. The other thing that will happen is your exhaust temperatures. If you've got a fire at the cylinder going in, right, is that going to increase your exhaust gas temperatures? Higher intake air temperatures is going to cause higher outtake temperatures. Agreed? And it's very localized. Usually this is not the whole scavenging air receiver. It's just where that coal fell out. It's usually 1 to 2 cylinders. So localized, you'll see a very rapid increase in exhaust temperatures on 1 or 2 cylinders. If you have a pyrometer or the electric thermometer in the scavenging airspace, that will come up. Now, in the older days, what they would tell us to do is to slow down, increase the cylinder lube oil to the affected cylinders. Your idea is, at this point, give it more lube oil in case that it is losing lubrication, you don't seize the piston. And you can literally, they would tell us to shut down the fuel injection, and on the big slow speeds, you can cut pumps out. Then you would wait till the fire went out, shut the engine down, and go in for an inspect. A lot of times today, they tell you to shut the engine down directly. When you go on a ship, you may want to check into what their procedures are. You may also have a CO2 system. I've been on ships that have a CO2 to put into the scavenging airspace for a fire. But a couple things I want to remind you on that. With CO2, you guys just went through, you're finishing up the firefighting this next week? Okay, but CO2 doesn't cool, doesn't it? It smothers. If you shut that engine down, believe me, there will be airflow through the engine and out the exhaust. You're going to have a couple exhaust valves and intake ports or intake valve open at the same time. There will be airflow. So if you discharge CO2 into that scavenging air receiver, it's going to blow in and blow right back out again. So one of the problems that you have with this is you literally, on the turbocharger, you want to take and put a canvas around the turbocharger inlet, right? Most ships, the turbocharger inlet looks like your MAKs on the ship, right? Attached right round and attached right directly to the turbocharger itself. It's a really good idea to have canvases made up and stowed for an emergency that you can pick up and wrap around the turbocharger. That will shut off air through the engine. You would love to do it to the stack too, but the reality of the matter is it's usually not safe to go up on the stack and try to put a cover on it, right? I don't know if you've done it on the Bear, but I don't think it's easy to do even sitting at the dock, right? So if you're dropping CO2, one of the things you want to make sure of is that, that you shut off air delivery through that engine prior to delivering the CO2. Because if you dump the CO2 immediately, you're going to blow through. The other thing on this, I want you to remember, if that engine shuts down at full sea speed, that propeller will run for probably 3 to 5 minutes before depending on the vessel type, before the engine stops. Direct drive, agreed? Most of these most of the main propulsion engines out there are direct drive. You've got a 20-foot, 30-foot diameter. That's a tiny little prop out here, right? That's a T2 tanker. That's a baby. You got this big prop out the back, and you're moving 20 knots. That's a lot of force to keep that engine revolving. So the engine has to stop, and you have to reduce the airflow through it before. Now, the other thing on this is there are drains on the scavenging air spaces. You got to make sure that those drains are always open. Now, on the older engines, it's about a 3/4 inch brass line, right? And you'd see them coming down the engine on the crankcase. And it's got a 3-way valve. One position, it's wide open, and you leave that open in port so that stuff will ooze down into the sludge tank, right? Out at sea, a 3/4 inch line at 45 pounds boost, that's a hell of a lot of air delivery. You change it where it puts a little orifice plate in there, right? So that it'll reduce the airflow but still have enough velocity to carry the sludge down. Problem with that, it doesn't take much to plug that up, agreed? So you would flip it once a day, you would flip it upside down, was the third position, to blow the crap out of the orifice and then put it back. And that was a daily job on the older ships. the newer ships, and that's what this is showing right here. That's what they're depicting. The new Burmeister wing, this line is direct down into the sludge tank, and the orifice is on the vent. That's a good thing to know, because a mean trick I can think of is to tell a cadet to go over and sound that tank when you're out at sea and it's pressurized to full boost, right? Or if you do it inadvertently. Does it matter that you know stuff? Can it affect your life in a positive way? I've never had anybody come up and say, I'm going to penalize you for knowing too much, right? Knowledge, don't ever think that knowledge is not power. You are paid what you get paid when you come out of here for the knowledge you have, right? But anyway, so think about that. And again, even like when we're going through all of these, I'm talking generalities, and there's a lot of different engines out there, right? So I'm trying to introduce you to general concepts. But you're going to have to dig down a lot deeper than what I can give you in this classroom. So always make sure these drains are open. That's one of the primary ways to prevent a scavenging air fire. Both of these can be exacerbated in the crankcase or the scavenging air fire if you have a poor combustion of any sort. By the way, that can also be a plugged up charge air cooler. That can be a bad exhaust valve. That can be low compression, bad rings, right? You want to stay out of this situation where you could have these bad things happening. You have to maintain the vessel. That one that we just saw on the British Velour, that is a direct result of incompetence. Bad injector, that would have affected their combustion, smoke, high exhaust temps, all of those indicators they ignored until they had this explosion, and then when the explosion happened, they got a secondary explosion because they weren't maintaining their explosion doors. That should have been a minor event. Well, it shouldn't have ever happened, right?